Question: can this music be random? No, it can't be. Why can we know that it is not a random sound that coincidentally sounds like music? Let's find out what random and not random is. How about these four? Are these random? Number 3 is not random. It's clearly a message. It's information. Number 2 has a pattern. We can see that even when we don't see what it is. It's actually a snippet of a bitmap file. That's a computer image. It's this image. Number 1 is generated using a randomizer. So that one is random. Deliberately random in this case. Number 4 looks just as random, but it isn't. It's a snippet of a JPEG file. That's a computer image. It's the same image as the bitmap file, but it's a lot more compressed. So it looks random, but it is very not. And this? Is this random? No, and we can see that when we show it like this. This is the Arecibo message. It's a file of about 210 bytes. It's a file that scientists sent into space in the hope that aliens will someday pick it up. If they exist. Scientists have agreed to send this message because aliens would be able to know for sure that it's not random. It's a piece of information. So why exactly can we know things are information and not some random signal? Is it because it is ordered? These snowflakes are clearly ordered. They are ordered in a very beautiful configuration. But they do not contain information. So order alone is not enough. Physical processes can create order, not information. So what is information? Information has 3 components: a sender, a message, and a receiver. If all 3 are in the process, information is involved. And the information itself is in the message. There are multiple ways to recognize information, even if not all 3 are available. One example: we can recognize information when we understand the message. Now for some more details. A medium carries the information, but a medium does not produce information. That's the sender. And in some cases there is a package to protect the information, so that random processes cannot easily damage the message. If we want the chance of damage of the message even smaller, we can do that by using a backup. So when we find information and also backups, we know undeniably that we have found information. There's another way to recognize information. When we see something passing from a sender to a receiver, and the receiver responds in a way that somehow makes sense, we can be sure that information is involved, even if we don't see or understand the content of the message. Information demands intelligence. Why? Can't there be random messages? Why can scientists know for sure that when aliens would pick up the Arecibo message, that intelligent beings like us must be the sender? Because if you put an ape behind a typewriter and you wait long enough, he could just type a book of Shakespeare coincidentally. After all, if we wait long enough, anything can happen, right? Take 2 cups of water. Fill one of them with a lot of water and another one with a bit of water. Then connect them with a little tube at the bottom. Then the water will flow from the more filled cup to the lesser filled cup. And that will continue until there is a balance. We can wait billions of years, but the water will never flow uphill. So no, it's not true that anything can happen given enough time. So what if we put an ape behind a typewriter? Let's see if we can calculate how long it takes before we get a book of Shakespeare by chance. To do so, let's see how chance works. assume we have 10 rooms with 10 apes. And they're going to type numbers from 1 to 10 randomly. And all of them are going to type a unique number. Apes don't do that, but we just assume it for this example. Let's just call them randomizers. Now pick a random number between 1 and 10. How large is the chance that one of them will contain that number? It's 100%, because all of the numbers are in there exactly once. If we let them type numbers between 1 and 20, the chance that you pick up a number that's in there is 50%, because half the numbers are in there. This works universally, so we're going 3D. We're going to make 1,000 rooms by dividing a box into 10 by 10 by 10 pieces. And then we're going to let each of them generate a unique random number between 1 and 2,000. The chance that one random number between 1 and 2,000 is somewhere in there is again 50%, because half of the numbers are in there. Now we're going to add time. We are going to let all of them generate unique numbers 10 times. Then we have 10,000 unique numbers. So if we let them randomly generate unique numbers between 1 and 20,000, the chance we pick a number that's in there is again 50%. With the random number between 1 and 2 million, the chance reduces to 0.5%. And when we make the number larger, the chance reduces together with that. This was a small box. Now let's use the entire universe. Scientists say that the diameter of the known universe is 93 billion light years. It isn't a box, but for this calculation it doesn't matter. So how large is 93 billion light years? Well, there are 365.25 days per year, 24 hours per day, 3,600 seconds per hour, and light travels 300 million meters per second. Multiply all that, and then we get the diameter of the universe expressed in meters. Cool. Meters. Why meters? We can go smaller. Why not millimeters or micrometers or smaller? How small can we go? Scientists tell us that the smallest unit possible is the Planck length. It's really small. There are quite a lot of Planck lengths per meter. There are more Planck lengths per meter than that there are meters in the observable universe. And so now we have the diameter of the universe expressed in Planck lengths. Cool. But the universe has a volume. So we need to do this value to the third power. And then we have the universe expressed in cubic Planck lengths. Let's call that cubic Plancks. But there's also time. Alright. So how old is the universe? Scientists say it's 13.798 billion years old, and we could debate whether or not this is true, but just let's assume this value for this calculation. Who cares? How old is that? Well, there are 365.25 days per year, 24 hours per day, and 3,600 seconds per hour. So this is the age of the universe expressed in seconds. Cool. Why seconds? We can go faster. Milliseconds or microseconds, or what's the fastest? That would be the Planck time. That's quite a short time. So here we have the amount of Planck times per second. And here we have the age of the universe expressed in Planck times. We can multiply that by the cubic Plancks. And now we can say that there have been this amount of cubic Planck times in the universe until now. A bit of a weird unit and quite a huge number. So what exactly does this mean? Well, it means we can give every indivisible time in every indivisible space in the universe a unique number between 1 and this value. So if we would stack it with extremely fast randomizers, we could get it all up to that number if we would use every part of the universe for as long as the universe exists till today according to scientists. This value is smaller than 2 to the power of 818. This number can be stored in a file of 103 bytes. So if we would be able to make the universe as a complete ultimate randomizer, it could randomize all possible unique files with a length of 103 bytes once. The erasable message is 210 bytes. So if we would let the ultimate randomizer generate files of 210 bytes, the chance that it would generate this message once is smaller than 0.00000 and a lot more zeros, 65%. So the chance is 0. So the chance that an ape writes a book of Shakespeare accidentally is quite a lot smaller. It's absolutely impossible. Conclusion: we don't have enough apes. For the books of Shakespeare, we need Shakespeare. Information demands intelligence. Any piece of information larger than half the erasable message cannot be formed by chance, and so it demands intelligence. To put it more generally, any random process that is not part of a sender cannot add information. Instead, it will damage it. Example: we have a piece of paper with a message written on it. Then a bird poops on it. Even if that has the shape of the letter L, it actually damages the message. DNA then. Our cells contain information. Yes, it's information. Why is it information? Because we see it produces very useful products. It has a sender, it has a receiver, it makes sense, so it must be information. It's as much as an encyclopedia of information in our cells. It's way too much to form randomly. Evolutionary theory says this formed by chance anyway. How then? Well, the theory says that it formed in portions. Small pieces of random information are added every time. Let's see. Our DNA contains several components. Parts of it is coding. That's the part that codes proteins, which in turn are the building blocks of life. Other parts are not coding, so it doesn't produce proteins. It has been assumed that the majority is junk. Recent studies clearly refute that, however. There's also a part that is clearly processing instructions. Let's focus on the part that everybody agrees upon. It's the coding DNA. So it's like a recipe for a protein, which are the Lego blocks for life. The longest protein code is 2.5 million nucleotides long. It's easy to say that that would be impossible to form by chance at once. So let's take a much shorter one. One of the shortest protein codes is 500 nucleotides long. Let's see if this one can be formed by chance. A nucleotide can be considered a genetic bit, just like in computers. But instead that it could be only 1 or 0, it can be 4 different values: A, G, C or T. So a code of 500 nucleotides long could have 4 to the power of 500 different values. That's 2 to the power of 1000 different values. This protein code can be stored in a computer file of 125 bytes long. We've seen that the ultimate randomizer could generate files of 103 bytes. So this is larger. So the chance that the ultimate randomizer could generate this protein code is quite small. It's actually impossible. And then we didn't even consider that genetics contain protons, which are a lot larger than the Planck length. We also didn't keep in mind that the majority of the universe is empty. Also, the Planck time is way too fast, and the majority of the materials is inside stars, so it doesn't produce genetic codes. So we're coming closer to the chance that a small protein code forms by chance. And this would be the chance if all the rest of the universe would be organic material, which isn't the case, and all of it would be constantly forming DNA code for more than 13 billion years in optimal conditions. Now let's be fair. There are shorter protein codes. Here's a well-known very short protein code. It's 157 nucleotides long. With that length, there are 3.33 times 10 to the power of 94 possibilities. And this is one of them. So yes, the ultimate randomizer would be able to generate it. But what about Earth? Could this happen on Earth? Let's calculate that. For this calculation, we pretend that the entire Earth consists of organic materials. This is the amount of atoms in the world. Then each atom must try quite a lot of possibilities. If we divide that by the amount of seconds that have passed according to scientists, then we see that each atom must try a whole lot of possibilities per second to find this code. And that would be if each atom would have its own code, which isn't the case, because one code consists of quite a lot of atoms. The speed displayed here is a whole lot faster than the fastest computer on Earth can count. Really, DNA isn't that fast. So if we would stack the entire universe with this material, it would probably find the code randomly. But any planet wouldn't. But even if it would then life have originated randomly? No, then we would have a protein code. We would not even have the protein, just the code. And now let's see what this code is for. Insulin. So let's assume that this code would somehow accidentally get translated into a protein. This can't just happen, but let's assume it. Then what would we have? Life? No, we would have insulin. Insulin is a complex chemical, a hormone. It's essential to us. People suffering from diabetes don't have enough insulin, so they can inject some insulin with a pen like this. Without insulin you die. But insulin alone does not live. It has no reason to begin with the process of survival of the fittest. So the code would soon disappear before it's used by anything. The chance that there is another user code nearby at the same time is again equally small. So for the chance that life pops in existence, we need to multiply the chances of all individual protein codes involved for that. So it doesn't help to say it formed step by step. It all has to be there at once. One scientist has determined that it would require at least 1500 errorless steps for a code to be able to copy itself. That's 1500 bits. That's a lot more than the 1000, which is the maximum for the ultimate randomizer. The smallest known DNA sequence in an organism is in a parasite called mycoplasma. It's more than 500,000 nucleotides long, so that's a whole lot larger. Random genetics can be produced in a laboratory, but like we calculated, this is not enough. And we would want an entire ocean of the stuff to have existed in the past, to make the chance of a useful code larger than in a laboratory. But there's a problem with this stuff. Shake it and it's gone. So again we can conclude we don't have enough apes. Useful DNA cannot form by chance. We're almost there. There are scientists who say that genetic algorithms solve the problem. There are pieces of code that automatically produces useful code. There have even been made computer programs that simulate that. But for that you need a genetic computer program. Let's take an example. Here we have the genetic algorithm framework. It's 146,000 bytes, so that doesn't help much. The smallest genetic algorithm isn't smaller than the smallest protein code. And by the way, who made genetic algorithm framework? An ape? No. So it still demands intelligence. So if DNA would be intelligently written information, we should recognize some protection, backups and repair systems. Well, there still is a lot to discover in this field, but repair systems have been found in DNA, and those are very, very complex. Can repair systems be random? No way! There are also a lot of backup systems in DNA. For example, chromosomes come in pairs, and every chromosome contains the information twice anyway, because the nucleotides come in base pairs. So every piece of genetic information exists 4 times in your body. And this is just one example of backup systems. There's an exception to chromosome pairs. The male Y chromosome is not paired. It's only one chromosome that is copied identically every time. Computers have read the code from front to end, and it appears that the Y chromosome is very special. It contains palindromes that hold all the information at least twice. Some information is in there even 8 times. That's an impressive backup. So here's the final conclusion. DNA is clearly information, and it can absolutely not be random.